The idea I'm getting ready to show you is an idea that was discovered by Leonhard Euler, at least proved by Leonhard Euler. It leads to something that's known as Euler's identity, which unites several of the most notable numbers in mathematics together. It basically combines some of the work that we have done with polar form of complex numbers, specifically cosine I sine form, with some of the series work we're doing. In this case, something having to do with the e to the x series. Okay. In your packet, at least if you're watching this having done the packet for my class, what you're asked to do is to evaluate e to the 2 pi I using the series representation for e to the x. All right. So background here, what's that going to look like? Well, the series representation for e to the x, of course, is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. All right. So our input here is going to be 2 pi I going in place of the x here. So I think I'm just going to go ahead and write it out here. So e to the 2 pi I is going to be equal to 1 plus, I'll have 2 pi I, plus, it'll be 2 pi I squared, plus 2 pi I cubed. Okay, and actually I'm going to continue this out quite a few terms because based on the way I'm going to show this, it's going to be tough to see it if you don't see quite a few terms. So then we have 2 pi I to the 4th over 4 factorial, 2 pi I to the 5th over 5 factorial, 2 pi I to the 6th over 6 factorial, and I'm guessing I'm probably getting off the screen here now. No, I've got a little bit more room. Let's do plus 2 pi I to the 7th over 7 factorial, and hey, let's do the 8th power one as well. Okay, what I'm going to try to do here is I'm going to try to simplify this down, and I'm going to use the idea. Remember that I to the first power, of course, is just I. I squared is -1. I cubed would be I to the first times I to the second, which would be -I. And then I to the 4th would be I squared times I squared, which would be +1. I'm going to use that relationship here to do a little bit of simplifying. We're going to look for something, all right? So, so here's what we've got. We've got e to the 2 pi I is equal to 1. I'm going to leave this as 2 pi I. Okay? I'm going to write this, this is 2 squared times pi squared times I squared. I squared is -1, so I'm going to write this as negative, and I'm going to leave the 2 pi squared in the 2, but I squared is -1, so we'll flip a sign there, okay? Now this, I to the 3rd power is -I, so I'm going to do minus 2 pi cubed over 3 factorial I, all right? And then I to the 4th power is 1, so I'm going to do 2 pi to the 4th power over 4 factorial, okay? I to the 5th power is equal to I, so that would be plus 2 pi to the 5th times I over 5 factorial. I to the 6th is the same thing as I to the -2, which is -1, so that's going to be minus 2 pi to the 6th over 6 factorial. I to the 7th, same thing as I cubed, which is -I, so that's going to be minus 2 pi to the 7th times I over 7 factorial. And then finally, I to the 8th is the same thing as I to the 4th, which is the same thing as 1. So that's going to be plus 2 pi to the 8th over 8 factorial. And that continues on infinitely, all right? So my claim here is that you should be able to recognize a series here, except that you probably can't. What I'm going to do here is I'm going to group. You'll notice about half of these terms have i's, and about half of these terms don't have i's, okay? So I'm going to take the terms that don't have i's, okay? That would be a 1 minus a 2 pi squared over 2 factorial, okay? That would be a plus 2 pi to the 4th over 4 factorial. It would be a minus 2 pi to the 6th over 6 factorial. It would be a plus 2 pi to the 8th over 8 factorial, and so on and so forth, okay? Now, that's only half the terms. Those are the terms that have just whole number values or real number values, no i's. okay? So it's going to be that series plus all of the I terms, okay? So we'll do plus 2 pi I minus 2 pi cubed over 3 factorial I plus 2 pi to the 5th over 5 factorial I minus 2 pi to the 7th over 7 factorial I, and so on. All right? And I can actually factor the I out of each of these terms, and I'm going to do that. I'll divide everything by I, and I'm going to put the I out in front of parentheses. Okay, so every term out to infinity is getting multiplied by I. All right? Now, if you take a really close look at this, and it's a little bit tough to see because of the 2 pi's in here. Remember, the 2 pi's are in place of the input. Okay? So if you think about what series you have here, you really have 1 minus x squared over 2 factorial plus the input to the 4th, x to the 4th over 4 factorial, minus the input to the 6th, x to the 6th over 6 factorial, and so on. Okay? What you've got is an alternating series. Kind of looks like the e function, but it's alternating terms, and it's just the even powered terms. It's the 0 power terms, 2nd, 4th, and so on. That is the cosine of x function, except it's not cosine of x, it's cosine of pi, because I put pi in there, okay? And the second series down here, you'll notice these are odd powers and an alternating series, okay? So that would be basically x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. The odd powers are the sine function, okay? But it's the sine function being multiplied by I, okay? Actually, I'm going to write this. So the first one was cosine of, should have been 2 pi, okay? The second thing here, that is the sine evaluated at 2 pi. But the whole thing is being multiplied by I. And what we end up here with our series, we end up with cosine of 2 pi plus I sine of 2 pi. Okay? If it's been a while since you've worked with cosine I sine form, just a reminder about what's happening here. What's happening here is, remember the form is r cosine of theta plus I sine of theta. Okay? R is the modulus, absolute value of the function, that kind of thing. So you can factor out a 1 here. This is saying I have something with a length of 1 that plots at 2 pi radians, okay? 2 pi radians, if you rotate all the way around, would take you right back here. The absolute value would be 1, okay? What are the coordinates of that? That's 1 plus 0i, if I have a real axis and an imaginary axis, okay? Or you could just evaluate this. Sine of 2 pi is 0. That goes away. Cosine of 2 pi is 1. Anyway, long story short, e to the 2 pi I is just going to work out to equal 1, okay? Mind-blowing concept here. Really, really, really deep idea in mathematics that unites a bunch of areas together and is used in a lot of different fields in higher mathematics. Really huge conclusion that Leonhard Euler came to here, okay? So by the way, to put this together, what we actually have here is this unbelievable fact that e raised to the 2 pi I power is equal to 1. And we unite some very powerful numbers in mathematics. 1, e, pi, and I all united in the same formula. Now, Euler did a different version of this. Euler actually did, the version that's known as Euler's identity actually shows that e to the pi I is equal to -1. So his version is that e to the pi I minus 1 is equal to 0. And then he actually links 0, 1, I, pi, and e, which I think even takes it a step further. Okay? I'm going to show you in another video where this idea comes from. But anyway, just mind-blowing. The first time I saw that, to just see all of these different ideas in theory come together at the same time, it's pretty crazy stuff.